So hi, let me start with a very striking fact of the world that in 2012 there was 14.1 million of the new cases where 8.2 million career cancer-related deaths is already been in the worldwide. That is based on the NIH. But the more striking fact is that though there is an extensive amount of effort and studies been performed for several decades, NIH predicts that it will be 2030 it will be like 23.6 million. So that's a kind of a shocking fact. And I think as an engineer or a controls and for all the intelligence system community, we have a big role to play. So myself, Hritwick Banerjee, I will be speaking over here on the more on the compliant soft robotics on the biomedical application. I think it's a kind of moral obligation for all of us to put hands on hands and then do a much better future on the healthcare activities. So a brief overview of my education and research experience. I graduated with masters from IIT, and over there I worked actually in ultrasound-induced biological cell characterization, mechanics and therapy, though my background was like electrical engineering. Then I went to Indian Institute of Science, over which I worked on the microfluidics platform of biomolecules and electroweighting. And then finally, I was right now in National University of Singapore working mostly on the hardcore soft compliant robotics, soft actuators, flexible sensors, wearable healthcare from the last 3 years with an affiliation from the MIT as well as Synapse. So main fundamental question is what exactly is soft robotics and where we can pinpoint it into the whole field of robotics. The main thing is we can even think of in 1980s or 1990s, even like early in 2000, on the left hand side, that is the rigid robot components we have seen. But from the motivation from the nature or the biological interface, we can see like only the soft and compliant bodies. Even our human body is almost like, if you can characterize, it's like 84 to 85% is the body fluid and the soft compliant thing. So we have combined the rigid component with the motivation of nature. Will have this kind of soft flexible robots that will be mimicking the biological entities for the future generation. So the next one is, so the main question from the polymer standpoint or from the engineering standpoint is, if we have a soft biomedical robots to be applied on, especially for the healthcare application, the main platform in which we usually play with is the silicon elastomer, or we popularly call as EcoFlex. But the problem over there is it is generally hydrophobic and it cannot retain much of the fluid, which our body fluids usually retain a lot of fluid. It is highly viscous and it is less responsive to the external stimuli, and chemically it is very inert and sometimes it's toxic as well. So I was thinking for quite a long time, can I have a solution for the fundamental way of looking at the soft robotics? And I think I found the answer. So it was actually in the hydrogel community. From the biomedical standpoint and the biological standpoint, it is more on the biocompatible and biodegradable polymer, in which it can be applied on the higher biocompatibility as well as the higher biomimicry. So the point in which I want to make a region of convergence from engineering's way is the artificial organs, drug delivery and the surgical device, which can be easily be utilized from the hydrogel standpoint. And the hydrogel that we have started to prepare right from scratch was like double network hydrogel, and I found some interesting results actually, which is already published. And I found out that on the silicon side, the maximum tensile strain it is able to achieve before it like break down in between was like 400 plus, where in my hydrogel it was able to find out like nearly 1800%. So it is already been published over there. And so in the whole spectrum, from the Young's modulus point, from the left hand side, which is like a very soft, to the right hand side, which is like very hard, where the hydrogel I fabricated is actually sitting in between the point in which is the agarose gel, the human skin, and as well as the porous component. So it has a huge, nice impedance matching with the body fluid as well as the body tissue. So the important thing from this hydrogel point, we have already fabricated this for the soft biomedical robots. And this biomedical robots for the hydrogel, we actually have a motion generation in between which has 3 degrees of freedom from one to another, and the maximum amount of angle we are able to achieve is 145 degree, which has been already used in the clinical point of view, and we have already done the cadaver experiment to show that it is actually happening inside the body. So that is, and after that, from the double network hydrogel, I was able to thinking of, okay, it is able to retain a lot of water, but is it able to have the reproducibility nature when it is drying out? So I have some sample with me which I fabricated the fresh hydrogel sample, which was like completely dehydrated. Yesterday, back in my, actually in the hotel, I put inside water and it forms like this kind of gelatin format. And I can bet you, if any one of you can come up and break this component, which is like completely dehydrated hydrogel, I'll be giving you whatever you feel like. So the thing is, this new hydrogel component which we built is like, it can see like an 800 Newton of load, the compression, and even after that, it is like perfectly alright. On the right hand side, you can see, it is able to go for 2128%, that is like 21 times, and that is only because of the reason because my machine's limit actually fell, but my hydrogel doesn't. And it is actually now in preparation for science robotics. And then another stand from the control community or the actuation principle. So we are trying to have a shape memory alloy which is being interfaced inside, and we will be having a biocompatible polymer as a kind of wrap up to have a kind of a actuation policies inside the body to see whether how much it can flex, and it will be used for the navigation and surveillance community for the surgical robotics application. So the main cool thing over here is like this hydrogel has a very self-cooling behavior. You can see on the first part over here, when it is being actuated in the bare shape memory alloy, it is like going from 0 second to 5 seconds, the temperature is plus 371 degrees centigrade. While it is being wrapped up with a biocompatible hydrogel and put inside the body, not inside the body in an ex vivo condition, it was like, even it was going plus 1 degree, then it came like minus 1 degree to come like a very nice on the room temperature and all. So this is also in preparation, and we are sending it to advanced functional materials. And now the thing is, from the intelligence community will ask like, okay, you built this kind of a passive component and then try to make it an active component, but if I cut it down to a milli range or even like a lower spectrum, can I have kind of a motion over there so that I can have a kind of wireless control to be sent inside the body for kind of a controlled application? So that on the left hand side we have our prototype which is like mimicking the smart skipper, and we have a relatively rough good displacement right now. We are building even more to have a nice displacement on the body fluid. And another thing is like the hydrogel endoscope is one of the things, like we have the balloon endoscope which will be inside the body, we can use it, but there is not a kind of a simulation from the finite element modeling, or even the control community can ask, is it possible to have a kind of mimicking control so that we can control from outside? It was the reason was like, it is like in a theoretical perspective, it is having an infinite degree of freedom and it can flex like that. So it is not easy to do that. So we are trying to have a mimicking finite element modeling to have this kind of balloon actuator inside the body, which you can know like for balloon actuator has been very highly used inside our body for the endoscopic purpose, balloon endoscope. And then I was thinking like, okay, I have seen people, even the kids usually come to our university and I have seen they play with the Lego. So that is like a very fundamental block of they are very joyful and all. So I was asking them, can I take some of the Legos? So I was making a kind of platform in which it is like a modular, and at the same time I can have this kind of a Lego bricks to make a kind of an actuator on the left hand side, you can see. So then on the sensor side, that is We are also building a kind of a soft flexible bend sensor in which this is a solenoid bend sensor. We are having a roughly good amount of inductance change, and based on that we can have a motion and to understand how much is the finger is changing when a patient is being suffered by a stroke or like a Parkinson's disease or by some kind of problem in which it is being paralyzed in one of the body. So we can try to understand whether through this one is able to do that. Then we found some kind of origami spectrum as well. These are already published, and for the sake of time I'll not go in depth. And then this origami inspired thing we have used for a surgical retractor. And there is another side of the project which is like for the soft robotics in which dielectric elastomer we have used to be used inside implantation for the aorta. There is like for cardiac